So today's objective is to learn about balanced and imbalanced forces and how they relate to motion. So you should be on page 153 of your notebook. You should have the essential question on your Cornell notes, because some of you haven't gotten lazy and stopped doing the essential question. That's supposed to be up there. Okay? The essential question is, how are forces related to motion? So, remember that when you take notes, I have an outline up there. That does not mean that you're copying every single word. Remember to abbreviate, to put in your own words. Okay? So, let's start off by talking about what is motion. Well, basically, motion is basically just a change in position. Motion is a change in position. Basically, if something moves from one place to another, you know it moves. And you don't even have to see it move. So if I'm inside the house, and I go to my window, and I see a car beside a tree, and I go in, make myself a sandwich, and I come back to the window, and the car is no longer in the tree, by the tree. Do I know that it moved? Did I see it move?
No.
No. But because I have a frame of reference, which is a tree, then I know it moved. So, motion is just a change in position. Be it you see it or not, if it's not in the same position, it moves. Now, there are several properties of motion. First of all, if something moves, it has to move a distance, right? So, a distance is just how far an object moves. So if I say 5 meters, is that a distance? 5 centimeters, is that a distance? So distance will always have a unit of meters, centimeters, miles, kilometers. Now in this class, what unit are we always going to use?
Meters.
Meters, or some type of metric system. It could be centimeters, it could be decimeters, it could be kilometers. Will we ever use English system? No, we always use metrics. Alright, displacement is how far the object moves and in what direction. So, displacement has to do with the distance and the direction. 5 miles north, 5 miles left, 5 meters left. If you wanted to give me a way to get to your house, would you give me distance or you give me displacement?
Displacement.
Why displacement, Menard?
Direction.
Direction. You can't just tell me, oh, my house is 5 meters from here. Okay.
Meters.
I can probably see it 5 meters. But if you tell, let's say 5 miles. Can I see it 5 miles away from here? Nope. Do I know where to go? Nope. No. So you have to give me displacement, right? So displacement, you give the distance, but you also give the direction. Speed, something we've talked about before. Basically, it's just how fast an object moves. There's a formula for it. Speed is equal to distance divided by time. Bless you.
Thank you.
It's a formula you're going to have to know how to use, even though you don't have to memorize it, because it will be on your formula chart. But, I mean, you're going to use it so much that you're just going to learn it. Alright, so speed is how fast you're moving. Velocity is how fast an object moves and in what direction. So like, have you ever seen the weather reports? And they say that the wind gusts are like, 10 kilometers an hour. But they don't just say they're 10 kilometers an hour. They give you direction. They say 10 kilometers an hour east. So are they giving you speed or are they giving you velocity? Velocity. So velocity is whenever they're giving you how fast something is moving and in what direction. And then the last property of motion is acceleration. Acceleration is a change in velocity. So a change in velocity, either going faster, going slower, or turning. Remember we talked about this a little bit?
Yeah.
So acceleration. If I'm walking at this speed, and at this velocity, I'm going this way, and then I start walking a little faster, did I accelerate? Yes. So if I'm walking at this speed, and then I slow down, did I accelerate? In physics terms, accelerate, usually we would say decelerate, but in physics terms, it's acceleration. What if I'm looking at this speed and then I do this?
You're accelerated in.
I accelerate why?
Because you change direction.
Because I changed direction. Even though my speed stayed the same, my velocity changed because since velocity includes direction, okay, and acceleration is a change in velocity, you change direction, you change your velocity, which means you accelerate, okay? So, these two, when we talk about these two in calculation-wise, you calculate exactly the same. So if you're going to calculate velocity, you're going to do speed equals distance divided by time. The only difference between this one and this one is the fact that velocity has to include a direction. Okay? So, any questions over any of those? Yes?
So like distance and displacement has direction.
Yes. In distance to displacement, same thing, except for displacement has direction. Yes, perfect. Any other questions over this? Alright, so now, let's actually talk about forces. What causes motion? What forces cause motion? Basically, a force is a push or a pull. If something is pushing you or pulling you, it's a force. Now, when we look at forces, the unit of force is a newton, which is an uppercase N. And it's something that you've already kind of looked at whenever you were doing some of the energy problems. Now, forces are never by themselves. They're always in pairs or even more than that. For example, right now, you are exerting a force on that chair because you're sitting on it and gravity's pulling you down. The chair is exerting a force on you. The air around you is exerting forces on you. The inside of your body is exerting forces out. So all those forces are happening at the same time. So when we look at force in a system, we have to look at the total force of the system. That total force is called a net force. So, bless you. Net force just basically means total force. Because every single object is going to have more than one force acting on it all the time. Forces do not come just by themselves. They're always in pairs, at least in pairs, if not more. So, when we talk about forces and we're calculating forces, we're going to calculate the net force, which is the total force. And you're going to be adding them or subtracting them depending on how the forces are acting. We'll get to that in just a second. So since you have several forces acting on an object, sometimes those forces are going to be balanced, and sometimes those forces are going to be unbalanced. So what does balance mean, Liliana? What does it mean? What does the word balance mean? I'm sorry? You're right, but just say it a little louder because I can hear. To keep it kind of in place, okay? All right, Jesus, can you repeat that and add to that, please?
That they stay in the same place, but they're also like, let's say what was it? Balance could also be like equal, or like equal in force.
Okay, Alfredo, could you repeat that and add to that if you want to add to that?
So where it keeps each other balanced, like stay in the same place, and then it's equal force, and it's also that the two forces of each other, they're equal the same, and they come together, and that object is still.
Okay, very good. Antonio?
They're equal, but they also like cancel each other out.
Equal cancel each other out. Ivan?
Every force acting on it is equal.
Every force acting on it is equal, and?
There's no change.
There's no change in it. Perfect. All those were perfect answers. Okay? A balanced force is forces where they're equal, they cancel each other out, nothing changes because it's not going to move. So if that, I'm sorry? Yeah, it's no motion. So if that's balanced, then unbalanced causes motion. Very good. So when we look at balanced forces, what we're looking at is we're looking at forces that are equal to each other and cancel each other out, which is exactly what everybody said. So truthfully, do you have to copy all that, or should you just write the simple things that y'all just said? I would write the simple things y'all said. Alright? Balanced forces cause no motion. Basically, if we calculate the net force will always be 0. So if we look at this diagram, here I have a cylinder. It's being acted on by two forces. This force is moving to the right with 5 newtons of force. This force is pushing to the left with 5 newtons of force. So, are those forces pushing against each other? Yes. So if they push against each other, is that object going to move?
No.
And the reason for it is because when you calculate the net force, we think of this as, since they're going in opposite directions, then this is like, it's a negative force. Okay, think of it as minus. Okay? So since they're going opposite directions, I would do 5n minus 5n, which gives me 0. That's why the net force is 0. That's why it does not move. Yes?
This is like something else, but what would happen if you didn't put like the, what would it mean if it wasn't a capital N? Would it just be, what would happen? Or what would we call? You know how like it's 5n? What if it was just 5 lowercase n? Would it be the same?
No, the unit is always written in uppercase n.
Uppercase? There's no other a unit that's like
They're
this?
only measured in newtons.
No, it all. Whenever we talk about forces, the Newton is the unit of force, and it's always written as an uppercase n.
Is uppercase?
Yeah.
Okay.
Yeah, it's always written as uppercase n. Alright, so any questions here? So now let's look at the unbalanced forces. So if a balanced force, they're equal, they cancel each other out. Unbalanced forces do not equal each other, and they don't cancel each other out. So since they don't cancel each other out, they're going to cause motion. They're going to cause movement. So if we look at this picture, here I have a force of 10 newtons pushing to the right, and a force of 5 newtons pushing to the left. So once again, they're in opposite directions, right? So since they're in opposite directions, I'm going to subtract. So 10n minus 5n gives me 5n. So the net force is going to be 5 newtons. And it's going to move to the right. And why is it going to move to the right, Megan? Very good. So basically, he said that when you subtract them, since the 10n is bigger and is moving to the right, that's why the object's going to move to the right. Okay? So Antonio, could you explain again why it's going to move to the right?
Because the 10n has more force than the 5n. So that's why it's even.
Okay, very good. And that's what happened. So any questions on this? So now let's look at this other picture. So here I have an object, and there's 10 newtons pushing to the right, and there's 5 newtons pulling to the right. So now here you have forces that are moving in the same direction. So if they're going in the same direction, if they're going opposite, we subtract them. So if they're going in the same direction, what does it make
Add 'em.
sense? We're going to add them. Okay? So we add them, then it's 50 newtons, right? And it's going to move to what direction? To the right, because both of them are pointing that way, right? So, if both of these objects are the exact same mass, which one do you think is going to be moving faster?
No.
Number 3.
And the one at the bottom? Why do you think it's going to be the one at the
Could
bottom?
have
Because there's
It
more.
has more energy.
There's more force.
Okay. Has more newtons than
And it
the
has more
top.
force reacted on it.
Has more force. Doesn't that make sense? If I push on something harder, isn't it going to move faster?
Yes.
Okay. So force is always also going to be related to the acceleration or the speed of that object. The more force, the more acceleration, which actually gets us into Newton's laws, which we're going to look at tomorrow. Did it? Alright. Any questions over balance and unbalance? Okay, to finish these notes up for today, let's just talk about some different kinds of forces.
I told you.
And this is the end right here. So friction is a type of force. Okay? Basically, friction is everywhere. You know, it's a force that is created when anything moves. And what friction is a force that opposes motion. So basically that stops you, or this tries to stop you. There are several types of friction. Two examples of friction are static and air resistance. Static, we talked about before because we know that it causes an electric current. That's why you're able to shock people when you're doing this on a carpet. Okay? Air resistance.
Oh, what? Oh, yeah.
Friction causes air resistance. Now, you know this, you just never thought about it, in the fact that you've seen things fall. Okay? So, what makes things fall here on Earth?
Gravity.
Gravity. Okay? Now, does gravity act differently on different objects?
No.
So I hear a no, I hear a yes. Okay. So these two pieces of paper are about the same, right? About the same.
Oh, wait,
They're not
no.
perfectly the same. They're about the same.
No.
Yes?
Snow.
Okay.
Snap.
If I drop these two pieces of paper, is gravity gonna pull?
Yes.
Yes, right? Alright. So,
But
some of you are saying that gravity is the same on everything, and some of you are saying that it's not. Now, from the energy problems, whenever you did the energy problems and you had to put a number in for gravity, what'd you put?
9.8.
On 9.8.
9.8. Did you ever change that?
No.
So regardless of whatever it was, you always put 9.8, right? It didn't matter if it was a 1,000-kilogram roller coaster or a 50-kilogram man. You always put 9.8. So you always put 9.8. So let me ask the question again. Is gravity different on different objects?
No.
No. Gravity is exactly the same on every object. It is pulling on everything at 9.8 meters per second squared. Correct?
Yes.
So, if gravity pulls on everything at 9.8 meters per second squared, if I drop these two things, it should hit the floor at the same time?
Yeah.
I mean,
it will be that because
If there
one has the
wasn't
air
any-
It
resistance.
depends on the object.
If there
No,
wasn't.
but hold on. Gravity is 9.8 meters per second squared on everything.
Yes.
oh,
not
but
every-
friction.
It should hit the floor at
Jose's
exactly
right.
the same
But
time.
the
Maybe.
You still
Now,
got things
when I
acting
drop
on it.
these, does that happen?
You still got, you got things
It
acting
What
on it.
happened to the piece of paper that did not happen to the balled up piece of paper?
It
What's
floats.
it?
Air resistance was pushing it up. So.
that's what I had said.
Because they had like more of a
Okay.
flat surface.
Okay, but so what did it do? Explain
Watch the
to me
video.
motion.
Watch the video.
It fell down.
Yeah, that out.
Well, they both fell down.
Oh,
Explain to me the motion.
Air is
Almost-
pushing up on the paper.
Eric said it right. One was
When
more
this one
aerodynamic.
falls, the air
It's like a
goes around
parachute.
this.
That's why we have
So like a
parachutes.
parachute. Ivan?
The ball paper, like, I don't know how to explain it. Like this shape, the way it is.
Okay, but none of you are explaining to me the way they move.
This
Oh.
one falls
I don't know
straight
how to
down.
explain
and
None of you are explaining the way they move.
One fell straight down and the other one just floated in the air.
Flip flop.
One fell straight down, the other one did not,
Oh, I
right?
didn't know she
Now,
asked
you
that.
are correct. I did. I said, how
I
did
know. I
they
forgot that
fall?
you asked that.
Now, you're right. Because of air resistance, it did not fall straight down because it was being pushed by air resistance and it kind of waved to one side and to the other, right? So, technically, it didn't fall straight down. Now, if that piece of paper would have been able to fall straight down, would it hit at the same time?
Yes.
Yes.
If there was no air resistance.
If there
It's
was
like
air
dropping a
resistance.
human
Very
off a
good.
building and then dropping a
Hey,
human
if
with
you don't
a
have any
hang
other
glider.
force acting on it,
Or
it'll both
if you don't have any other force except for gravity,
it'll be the fault.
it's going to fall exactly at the same time. Now, is that going to happen here on Earth?
yeah. Wait, what are you
Like
talking about?
outside, could I get that to happen?
No, you have to have like a perfect.
No. I would have to have what we call a vacuum room, in which all the air is sucked out of the room, so you wouldn't be in there because you can't breathe.
But you
Okay.
you use like
How do you-
And
how do
it
you-
would
how
run
do
at the
you
same time.
How do you put things in the vacuum room?
you can wear a spacesuit.
Well, no. You put things in there and then you suck out the air after you're out of there. Usually it's not a room, it's a
You ever
little
seen those like
encasement.
plastic bags when they have like the vacuum thing?
Yeah, it's an encasement. You just
Oh,
vacuum
but
all
I mean,
air.
how do you do
Yeah,
your
the
work
clothes
in
that you
there?
can flatten out.
You're not in there. It's an encasement.
It's a little
That's
box. Look,
why.
look. It's
You're
a,
not in there. It's like a big box.
You're like
It's
on
in
the
front
outside.
of you.
and they have gloves that you put your
I
hands in.
understand that, but my point is like, how are you supposed to?
There's a machine that you push a button and it lets it fall.
Oh,
And look, and like you have those gloves that you put your hands
isn't
in.
that gloves? I thought it was that.
Alright. So any questions over these? Alright. So that is the end of the notes. They are Cornell notes, so don't forget to get your questions and your summaries done. Okay?